Have you ever wondered how the color spectrum works?
Yes!
Or why color is reflected or transmitted? What about sunlight? Or how mixing colored lights work? What about complementary colors? Or why the sky is blue and why sunsets are red? Well, in this video, Caroline and I are going to show you how all of those things work.
Sir Isaac Newton was the first person to make a systematic study of color. He successfully showed that sunlight is a mixture of all colors of the rainbow. Newton demonstrated this by passing a narrow ray of sunlight through a glass prism, which then reflected a spectrum, or all colors of the rainbow, on a white sheet of paper. Whenever a combination of all colors is shown, we call it white light. For this reason, white is not its own color, but a combination of all colors. On the other end of things, there's black. It's also not its own color and is known as the absence of light. An object will only appear black once it's absorbed all the light of visual frequencies. However, black objects we see every day do not absorb all light that falls on them, and there is always some reflection on the surface, otherwise we would not be able to see them at
all. All objects have different natural frequencies for absorbing and emitting radiation. This means that when the frequency of light shining on an object resonates with the object's natural frequency, it absorbs all light. So that also means that if the frequency of light shining in an object is higher or lower than the object's natural frequency, then the object re-emits the light. This is how we see color in an opaque object, like this shirt. It is absorbing some colors and emitting the color we see, so orange.
The color of transparent objects are the color that they transmit. For example, in a church full of stained glass windows, the sky on one of the windows appears blue because it transmits or gives off the color blue while absorbing all other colors that compose white light, which is Roy G. Biv. Similarly, the grass in the same stained glass window appears green because it simultaneously absorbs all other colors except green, which it transmits. We call the absorbing material in the glass pigment. In terms of atoms, we see that electrons selectively absorb light of certain frequencies and re-emit others, which we see.
Radiation curve. This is the graphical distribution of brightness versus the frequency in sunlight. So because of this graph, we know that the brightest portion of the spectrum of sunlight is in the middle range. So that would be yellow and green. The right portion is red, and the left portion is blue. Because of this, we know that the brighter it is, and the more frequency there is, you'll get purple light. And if there's low brightness and low frequency, you'll have red light. As we learned earlier, all colors of light mixed together creates white. Another combination that can create white is red, green, and blue. Mixing different light colors can create multiple combinations of light. For example, red and green on their own make yellow light, red and blue produce magenta, and green and blue make a teal light called cyan.
Here you can see all three colors adding together to produce white, and here is red and green producing yellow. And there are all three colors again. You can see cyan in the corner, and here is red and blue producing magenta. Now Caroline is going to tell us why this is helpful.
Red, green, and blue are known as additive primary colors. This is because you can create almost any color in the world by overlapping a combination of these three colors and adjusting their brightnesses. For this reason, all color television is shown using these three colors. The pictures on the screen are made up of an abundance of tiny spots that light up with different colors and brightnesses to create thousands of colors we see on TV every day.
Complementary colors are two colors that when added together make white. So this includes magenta and green, yellow and blue, and cyan and red. Try this at home. All you need is a screen-colored cyan, a piece of red tape, and your phone flashlight. Okay, so what you're going to have to do is put the piece of red tape over the camera of your phone. Then you're going to want to point it at the screen-colored cyan, and you'll see that the screen is white. And when you take the tape back off again, the screen is back to cyan. Using what we know about colors and paints, we know that if we were to mix red, green, and blue paint, we would not get a white color, like we would with white light, but rather a dark brown. As you can see here, red, blue, and yellow are being mixed together. Now, I don't know about you, but that doesn't look like white. So, Caroline's going to tell you why pigments are different than light.
Paints contain tiny solid particles of pigment that produce their color by absorbing and reflecting light of certain frequencies. For example, blue paint reflects mostly blue light, but also green and violet, which are known as cool colors, while absorbing red, orange, and yellow, the warm colors. Unlike using addition to make colors with light, pigment uses subtraction. We know that blue pigment and yellow pigment creates green pigment, but do you know why? The only color both blue and yellow reflect is green, so all other reflected colors are subtracted and we're left seeing green.
The three main subtractive primary colors are magenta, yellow, and cyan. Color printing only uses these three colors plus black to print every image you've ever wanted. The tiny dots of color are placed on the paper until they perfectly match the shade you're looking for. For an experiment, you can try looking at a colored picture with a magnifying glass and try to see if you can spot any of the different colored dots on the image. Want to know why the sky is blue? Well, the light is scattered, or absorbed and remitted in all directions. So this means that the smaller the particle, the higher the frequency and the more it will scatter. When there's many large particles, like larger than oxygen and nitrogen, the molecules scatter and the sky begins to look white, like clouds. Since they contain water droplets with a wide variety of sizes, the drops scatter and provide the cloud.
Have you ever wondered why sunsets are red? It's because lower light frequencies are scattered the least throughout the air, which makes red, orange, and yellow light more readily transferable than violet and blue. Since red light travels the slowest and does not interact with any other light colors, red is transmitted through a longer path, thus making the sky appear red.
The more you know.
Every element has its own characteristic color when made to emit light. The light is emitted when an electron is in an excited state, which is defined as an atom being in a state with a greater energy than the lowest energy state, and it's directly related to the orbit of the electron in the atom. The closer the atom is to the nucleus, the lower the energy level, and the farther away from the atom, the higher the energy level. Once an excited atom emits external energy it has absorbed, it returns to its normal state. The best spectrum will show when atoms are made to glow in the gaseous phase. Much of the information we have about the atomic structure comes straight from the study of the atomic spectra. The spectrometer is a tool that changed the way the world sees colors and the atomic structure. Yeah!